Hi guys, it's Luke, and today we're going to move on to chiral reagents. First off, we're going to talk about Mosher's acid chloride, which is the separation of racemic alcohols and amines. As you can see, we're going to start off with an alcohol or an amine, it doesn't matter which one we use really. We're going to add this Mosher's acid chloride and a base. This then makes these items here. This is basically using this OH. It's the same if we use NH, just obviously replaced by N. And we can separate these diastereomers via chromatography. We then move down to this step here, once we've separated them, and just add KOH, potassium oxide, hydroxide should I say, and we get this an antimerically pure alcohol. Obviously we could separate it this way instead, so we could have this product and get an antimerically pure alcohol there instead, but we decided to use this one in this example. Obviously, like I said, the same thing sort of happens with the amine. Now this is an important reaction mechanism, the Corey-Bakshi-Shibata reduction. Start off with this lovely compound here. It's fairly simple to draw, and it's usually given in exams. So we've got this compound here. We've got a large R group and a small R group. Obviously the small R group is going to be closer to this over here, but we'll get to that in a second. And that's the products that we form there with the 85 to 90% EE. So that means we've obviously got a high percentage of one and a very low percentage of the other. So this is basically a transition state. This is the important part here. We've got H3B still. We've explicitly drawn out one of the H's. This is our ketone that we've got here. Like I said, the small group is going to be wanting to point towards the butyl. That allows us to do this attack, and that's because it's obviously small, so it doesn't get blocked off by the butyl, whereas the large group would. So what happens here? Double bond on the oxygen attacks the hydrogen, which then comes back onto our ketone, back onto our oxygen of the ketone basically, and then obviously to remove our positive charge on the nitrogen, we just donate the electrons back onto the nitrogen there. That leaves us with basically that product there with no positive charge anymore, and we get this product as well. So the H just leaves basically, and we get this product here. Well, the H doesn't leave, sorry, the H bonds there, as you can see, and obviously we've not got a double bond now, and we coordinate to the boron as well. As I said, we get that as a side product. This could be reused as a catalyst, but it's better stoichiometric, and we're just going to add BH3 again, which obviously attacks at the nitrogen there, reforms the catalyst. But yeah, we add H0 plus, obviously a strong acid, and that just removes our boron there, which effectively that can reform. So once we've removed that with H3O plus, we can get H2O and BH3 again, which obviously these two can react together again. And yeah, that's how we reform that. Acts as a catalyst, our starting material effectively. Next up we've got this Davis oxaziridine. This is a, as you can see, complicated one. It contains sulfur and nitrogen. But there's quite a few reactions we can do with this. Mechanisms aren't seen for this part, but what we've got is we've got a trans alkene there, and all that does is forms an epoxide. Effectively, you can see what happens there. We attack this on the sulfur, and that's what we get. We get the epoxide. Next we can use this cycloalkene with the oxygen and the silicon on it. That gets this product here. As you can see, there's high EE fairly for each product so far. We get this product here. Not sure exactly how you make this one, I'm not gonna lie, but it must be involved in attacking the same same sort of places. And finally on this one we've got a mechanism. It's kind of similar to the Corey-Bakshi reagent or Bakshi-Shibata reagent. We can react that with a transalkene as well, and that attacks at the epoxide, and the epoxide can break again and basically forming one bond like there, one bond there. That makes the epoxide ring there, and obviously this ring breaks and forms a double bond with the nitrogen. It's quite a simple mechanism, that one. And yeah, that's pretty much it. Then we've got a couple more for chiral reagents. This is from our previous year's exam. We've got hydroboration here. As you can see, we pretty much got a borate acting like one of our organic cuprates. It's looking like an organic cuprate anyway, but the double bond attacks the hydrogen, and the hydrogen loses itself, I suppose, and that obviously just forms one bond to the boron, and then a bond from the boron to the thing, forming these two bonds here. After that, we just go for a H2O2 and NaOH, sodium hydroxide, sort of workup. That just removes our Br2 group, and we get a stereoselective alcohol there. We use DIP-H for chiral boration as well. This is just one of the products here. Very nasty to draw really, but it's something that's used for chiral boration, which you can see here. So the DIP-H that we use up here or there, once we've added the BH3, can be used in this case here. As you can see, we form enantioselective products from our E and Z alkenes or cis and trans alkenes, and yeah, we form an S centre there and an R centre there. So yeah, that's pretty much everything. Obviously this is 87% selective for this R, which means obviously the other 13% for the S for that one, whereas this one's 73% selective for the S and 27% selective for the R centre there. So that's pretty much everything for this. Next time, as you can see, we're going to talk about chiral auxiliaries, and there's quite a few reactions in this topic as well. Then after that, we've got one or two more videos to look at after that as well.